This is HRW910P056. We have a rod, massless, rigid rod with two masses on the ends. We have them bouncing on a fulcrum where we know the distance from each end to the fulcrum, and we want to know if we set it up horizontally and then let it go, what the magnitude of the initial acceleration of particles on each end, what they are. So I've already redrawn this over here so I can go full screen and we don't have to go back looking for stuff. So the first thing I'm thinking is, okay, it looks to me like this end is the end that's probably going to fall, because although each mass is the same, this one's further from the fulcrum. So basically what we have here is more torque on this side. So this whole thing is going to kind of spin like this. It's not going to get very far because it's going to hit the ground, but initially, I mean, that's what we're looking at. So think of this as the whole body is going to try and do this. Okay, it's going to try. So I'm going to get something angular out of this. So if I'm working with circles, I'm probably going to use the angular acceleration, torque, all that good stuff. Okay, and in fact, if I want to know the acceleration here and the acceleration here, basically it's going to be accelerating like this way, and this one's going to be accelerating this way. That's tangential acceleration. So what I'm really looking for are the tangential accelerations at each end. And tangential acceleration is equal to rotational or angular acceleration times r. So if I can just find, and I have r, that's the distance to the pivot here. I have those numbers. So if I could find this, yeah, let's go for that. If I could find that, I'll be awesome. It'll be handy dandy. Well, the only thing I know about, the only ways we could get this are either with a kinematics or with Newton's second law for rotational dynamics, which goes like this: net torque divided by moment of inertia. I don't have enough information to do rotational, so this is the only way I can get my alpha, my angular acceleration. So let's get those two pieces. The net torque actually is not so bad. I only have two forces acting. I've got the force of gravity on this thing, call that F, which is m times g, and I have the force of gravity on this thing, which also is m times g, because they're both m and gravity is the same everywhere. So I have two forces that are exactly the same, they're just applied at different places. They are also nicely perpendicular to my radius to the center of my circle, which will be here. So I won't have to deal with sines or anything, no angles involved. I can straight up do that torque, change color here. Torque in general is force times the distance to the center times the sine of the angle between them, but this, the angle is 90, so this is going to be 1. I can basically just ignore this whole bit, okay? I can just do FR. So in this case, for both of these, the torque is going to be mgr, so F is mg, okay? The thing is, they're in different directions. I know it looks like they're pointing the same direction, but the force is pointing the same direction. The torque is not. Torque, remember, the direction is positive in the counterclockwise direction, so this way. Anything that's torque is pointing this way will be positive, so that would be this one, okay? And then anything that is in the the clockwise direction is negative torque, so that would be this one, okay? So what I have is the net torque. My towels get really sloppy after a while, sorry. The net torque, we're going to go positive. Positive is mgl1. And then I'm going to subtract any negative torques. That's mgl2. Remember, I'm doing mgr for both. In this one, the r is L1. This one, the r is L2. Okay, I'm going to go ahead and pull that mg out just because I don't know. I like to factor things when I can. And that gives me with mg times the quantity of L minus L2. Okay, I'm going to leave that alone. I don't put numbers into the end if I can help it. I'm having a little slack on that lately. I need to go back to my physics roots. Stop being an engineer. Okay, so that will take care of this one. Now I need moment of inertia. Okay, so moment of inertia. Well, what I have here is I've got those two masses on a rigid massless rod, by the way. Let's make sure it says a rigid massless rod. Okay, so I don't really have a rod here, so I don't have to do like 1/3 mr squared or the 1/12 mr squared or any of the stuff that has to do with rods. Really, all I'm dealing with are these two particles. So all I really need is the basic moment of inertia equation, the one that looked like this. Okay, and I only have two particles, so what I'm going to have is the moment of inertia is the moment of inertia of one of those particles plus the moment of inertia of the other particle. That's all. And let's see, that's going to be m is m, okay, m is m, and r of this is L1, so it'll be L1 squared plus, for the other particle we have m is m and r is L2, so we get L2 squared. And that's it. So then the moment of inertia is I'm going to pull an m out to the front, and I get m times the quantity of L1 squared plus L2 squared. That's it. Now, I put all those together. Alpha. Okay, I've got my net torque was mg L1 minus L2 divided by my moment of inertia was m times L1 squared plus L2 squared. Oh, look, this is good. M's canceled out, which they better have because they didn't give us a number for that. Big hint, if they don't give you a number for the mass in any problem, it's probably going to cancel out somewhere. Just keep going. You can do it. All right. I have all of these numbers, so I can go ahead and find this. Okay, so for me, let's see, G is 9.8 meters per second. L1 is 21 centimeters. I'm going to put that in meters. Oh, you know what? I'm just going to leave that out. Minus L2 is 81 centimeters. Put that into meters. Let's see, L1's 21 centimeters. Got to square it. Plus, got to square it. I throw all that in my calculator. I will get a negative number. That's okay. I'll talk about that in a second. I get negative 8.3976. Even if I round to the nearest thousandth, like starts tripping over, and I get negative 8 point, what is that round? 40 is what I get. And that's still angular momentum, so that's why did I put an M? It's radians per second. Rads per second. Squared. Squared, gotta square it. Okay, just to note it, why is it negative? Because that means that it's going to rotate, or sorry, it's going to accelerate in the counterclockwise direction, which is this way, and that's the way we thought it would go, so we're good. Okay, now I have to go back way over here. Remember this? Way over there. And I just need to use my newly found angular acceleration, which is the same on both sides, because remember, for any rigidly rotating object, all of the angular values are the same all over the object. So that's the same for both of my answers, but the R is different. So for particle, I'm calling it particle 1, the one on the left-hand side, I use, let's see, AT is the angular acceleration times L1, which is 21 centimeters. Okay, so that's going to be, hang on, let's store that answer. There we go. Now I can times 20.21. I get negative 1.6, or sorry, 1.76 meters per second squared. And then that was for 1. For 2, I do the same thing but with that radius. So la la la. Okay. Nvar times 0.81 gives me negative 6.8. Okay. Where's my cursor? Okay. 6.8 0 meters per second squared. Okay, now the actual problem though asks for the magnitude of the initial acceleration. That's why the negatives have been chopped off. Okay, so I get 1.76 for the first one, check. Boom. And 6.8 for the second one, check. Awesome.